Are there any sort of bureaucratic questions you want to ask me just at the moment? For instance, okay, let's just talk a little bit about the organisation. It's 4 lectures a week, okay? So it's 4 hours a week. There's 3 hours lecture and 1 hour tutorial. So Monday, Tuesday at 12 o'clock. Thursday there's a tutorial at 12 o'clock, and Thursday there's a lecture at 3. There'll also be a practical, I think on Wednesday from 1 to 3, okay, and that'll probably begin in week 3, this being week 1. Okay, so I know the mathematicians and ethics people might have some issues with that, but let's see how it goes for a while. Okay, any questions about that kind of thing before we get down to business? Yes, sir. There will be a little bit of a tutorial this week, yeah, but what there won't be, do you remember there was a bit of confusion yesterday about the fact that I might be taking a 2 o'clock lecture belonging to Dr. Kokoran? That's because we're doing a swap. So he will be taking the Thursday 3 o'clock lecture for this subject, 3D1. He will be taking it this Thursday. So MSIS and mathematicians, TSMers, there won't be a lecture in this subject on Thursday at 3 as there normally would. Instead it'll be taken by Dr. Kokoran for 3C1, I think is the code for his his program. I actually don't know. I'm sorry, it's on the timetable, as best I can say. So just moving through this to find where we stopped yesterday. Course topics, okay? So just a little bit more of the old bureaucracy here. Coursework. Now this is a big deal, okay? So I want to tell you explicitly and definitely about coursework. There's going to be coursework. As you can see here, there's a tutorial every week on Thursday at 12. Location, I just can't remember. It may be in Ars an Phiarsaigh. It's on the timetable. There's going to be a 2-hour practical every week when we get started. We probably won't start until week 3. It might even be week 4 by the time we get down to business. And because of the size of the class, which is fantastic, it may be that we might have to break that out into 2 sessions in the week. We'll see how that goes in the next couple of days. The practicals are actually marked. So you have a 2-hour practical. You'll be given the assignments usually at the end of the week, on the Thursday of the week ahead of it. You have time over the weekend and the rest of the week and the weekend to figure out what you're going to do. You go in there, you do it, you get a mark for it at the end, you walk away. Okay? No handing in stuff afterwards. Now, there's actually, this is incorrect, so I'd like you to just take note of it. It says practicals will be marked with continuous assessment, which will be worth up to 15%. It'll actually be worth up to 20% of your course mark. So perhaps you make that note, and if I can, I'll make a change to these overheads later. Up to 20% of your UN mark. And I don't want to tell you exactly how much it is yet, because it will vary depending exactly on what practicals we get to do. Okay? Once again, I just want to say the coursework is very important. It's absolutely vital, because this stuff, as you may begin to appreciate when we get down to some of the detail in a few minutes, it's very logical. And you've seen it before. You've probably seen it in the Ladybird book of computers, and you'll certainly have seen a lot of talk about it in secondary school and in the media. The point is, though, that knowing about it and actually being good at it and doing it are really quite different. I don't want to be facetious, but it's almost like being an appreciator of music. You know, somebody who can appreciate a good tune or a well-organised or a nice band or something like that. And you say, oh yeah, I'm a real expert. I know the difference between Led Zeppelin and somebody else, right? Franz Ferdinand or something like that. Just to mention one. However, it's a very big difference between appreciating on the one hand and actually doing, constructing, making, writing, performing, if you like, music on the other. And you need to keep that in mind. This is very, very tricky stuff, and it seems logical, it is logical, but it's very tricky in detail. Okay? So the coursework is vital. And here is the sort of mandatory statement here. You must attend the practicals. If you don't attend the practicals sufficiently well, we reserve the right, in keeping with college regulations, to return NS. NS stands for non-satisfactory attendance at courses. And they have implications which you can read up about in the calendar if you wish, but they're pretty severe. They could include you not being allowed to sit exams in the summer, or all kinds of things like that. Not being allowed to proceed with your year. Okay, enough of that kind of stuff. Okay, a couple of references for books and textbooks. People gain a lot of comfort from having a textbook. And over the years, there are lots, like I said yesterday, there's lots of knowledge out there about teaching on the 68,000, and it follows there are lots and lots of books. Most of the books are aimed at American audiences, and they're very big, thick, detailed, books that are hard enough to carry around, never mind read through. Books that are aimed at a British audience tend to be much better. They're more compact, more concentrated, and generally better. And one is this Clements one here, Alan Clements. Okay, so have a look for that. Now, I'm not saying you should buy this textbook, but I'm saying go out and have a look, and if you can come across something like Clements' book, fine. There's another book by King and Knight. It's an old book. It's very thin, and it's something like Introduction to Programming with the 68,000, or 68,000 Programming Intro, or something like that. King and Knight, the two Ks. There's also some stuff, there's lots of stuff on the web. In general, you can Google 68,000 stuff, and you can also look on the website for this subject, and that's the URL for it there. Okay, so it's pretty logical when you think that this is a junior sophister engineering subject. The engineering degree is called the BAI. Okay, that's its principal aim anyway. Okay, so let's get down to business here. Okay. So here's something that you might recognize. We're not going to go much further than this. Yes, sir.
Sorry, what programming language are you using?
We're using 68,000 assembly language, so we're using no high-level languages at all. But just to be clear about that, because it's a very good question, we're not doing Intel assembly language, we're not doing 6800 assembly language, we're not using x86 assembly language. You'll see lots of these things out there. We're using specifically 68,000, Motorola 68,000 assembly language. Okay. And please ask me questions as I go. Okay, you'll appear on the podcast, but that's okay. Now, this is the typical ladybird example of a computer system, and I don't mean to denigrate it by saying that, but it was originally designed, if that's the term. It's a design principle really, rather than an architecture. And the design principle can be stated pretty quickly, and it is to separate special purpose units into special purpose devices, or special functions into special purpose devices. So in the top left there we have the CPU, the central processing unit, which is where everything gets done. Okay, all the calculations are done, all the instructions are executed. And in fact, considerably more goes on in the CPU than just in executing instructions, as we'll see. But it's specialized. If you think you're designing the piece of hardware, if you're designing the CPU, you only have to worry about that. You have to worry about fetching, decoding, executing instructions, and dealing with the data that's required. Another component of a typical computer system is memory. Okay, memory is again hardware that has the property of being able to allow you to retrieve information in a particular way. So you can get information from the memory of the computer into the CPU. Now that information in a von Neumann machine can be data, typically numbers or characters or arrays or whatever it happens to be, but it can also be the program itself. Okay, so that's one of the defining features of the Neumann architecture as opposed to other architectures. Data and instructions, data and programs can reside in the same component, the memory. Now there's two memory subsystems in this for the reason that most computers nowadays actually come with two fairly distinct kinds of memory in them, and maybe more as we might see later in the course, but two fairly distinct subsystems, one being what's commonly called RAM, RAM. RAM stands for Random Access Memory, and it is a misnomer. Okay, and we'll talk a little bit more about it. ROM, ROM, is read-only memory, which is not a misnomer. So here's the deal. The trouble with memory generally is that when the machine is not powered, or when the battery goes down or you unplug it, memory forgets or loses its contents, right? So a question might be, how do you get a computer to start up when you power it up? Where is the program going to be if memory doesn't work? Okay, And that's generally, but not always, but that's generally the function of ROM. Read-only memory is memory that cannot be altered by the computer, which isn't much use, but it's memory that retains its contents even when the machine is powered off. That's its important thing. So typically what happens when a computer of any kind starts up, a program in ROM, in read-only memory, gets control of the machine in a manner that we will explain later. It gains control of the machine, takes it over, and boots it up. So very often it's called boot ROM or boot memory. Okay, so once the machine has powered up, then perhaps you'll be loading, or the machine will load programs that it's going to execute, or it'll load data that's going to execute, and that information is stored in RAM. RAM stands for random access memory, but actually what it really means is read and write memory, read-write memory, memory that you can put stuff into, that the computer can store stuff in and retrieve it back later. Remember now, ROM allows the computer to retrieve information only. It can't put anything out there, can't change it, and it doesn't forget what's there when it's powered off. But RAM then is a place where it can hold things temporarily. Remove the power though, and RAM forgets what's in it. Okay. So typically RAM is much cheaper than ROM. Okay. So when you buy a machine, you might buy a machine with say 512 megabytes of RAM, or a gigabyte or 2 gigabytes now of RAM, and it might only have maybe 256 megabytes of RAM or less. Okay, ROM tends to be a bit more expensive. RAM then is a place, if you think of it like this, it's a place where in a mature and well-organized computer, like a desktop computer, for example, you'd expect that RAM is a place where you hold stuff temporarily for use, whether it's a program or pieces of data. Typically, your file structure, the file system that you get to know on a computer, is stored outside the computer system proper in something like a disk drive or on the network or something like that. Okay, so we have the CPU where everything gets done. We have memory where stuff gets stored. And then we have this other thing here, the peripheral interfaces. The peripheral interfaces, like I was saying yesterday, they have the physical job of mediating between some aspect of the outside world, as we call it, and the interior world of the computer. The interior world of the computer initially is a place where instructions get executed and data gets processed, right? So something in the outside world has to appear in that inside world as data. Okay, that's the function of the peripherals from a logical point of view. Physically, of course, they have to mediate say it's a temperature or high voltage or pressure or something like that that's maybe being monitored or being affected, and the peripheral interface has to do that. And I've just given you a couple of samples of peripherals that you might find on a desktop type or an office type computer. A screen and a keyboard, they're peripherals. Disk drive, that would be a peripheral. Network, say an Ethernet or a telephone network or something like that, that would be a peripheral. And the printers and so on, they would all be peripherals. Okay, so the peripheral interfaces, these are the things that we think of as the computer. Naively, you look at the computer and say, oh, that's the computer. But actually the computer is just the CPU, the memory, and the peripheral interfaces as they appear from the inside. Okay, so that's the von Neumann machine, the von Neumann machine. Von Neumann was I think he was Hungarian, but he is considered a physicist, an engineer, a mathematician, and a kind of a philosopher, depending on what you happen to be. If you're an engineer, he's an engineer, and so on. But a very smart guy to come up with this idea of partitioning the functions that are needed in a digital computer into special purpose components. Okay, so that's the von Neumann machine, and the 68,000 is actually a central processing unit in this kind of world. The 68,000 is a CPU. Okay, so the CPU then, just a little bit of detail on these upcoming slides on what's what. The CPU is where all the work gets done. Now, what does that mean? Well, that's where the instructions get executed. You'll remember from yesterday that what we'll be doing is writing instructions in assembly language, each of which turns into a machine code instruction, and each machine code instruction is executed in the CPU. Now again, this is very logical. Like I was saying earlier, this is very logical. Yeah, we know that. Okay. What are the implications of it? The implications of it are pretty serious. There has to be hardware resources to execute those instructions. because we're at the level, we're at the ground floor. Okay, beneath us is the hardware, and above us is other software. So these instructions that are coming in, as it were, in the ground floor, they have to be executed by the hardware. They have to be effective in that algorithmic sense. Right? So that's the first implication. So if you have an instruction, there has to be a bit of hardware there to execute it. Okay? But even more, a program is a series of instructions, and they're usually instructions that are stored in memory one after another, sequentially in memory. Roughly speaking, that's the case. If that's the case, then if the instructions that are going to be executed in the CPU live in memory, in RAM, we'll say, or ROM, then they have to come across that bus that I didn't mention. Oops. They have to come across that bus into the processor to be executed. So anytime an instruction is going to be executed, it has to be fetched across the bus, has to be brought into the CPU, it has to be put somewhere, it has to be deciphered or decoded by the hardware, and it has to be executed. Okay, it has to be given effect to. If the instruction uses data, the data must also be in the CPU. Okay, so there's a lot of implications from the simple idea that the CPU is where all the work is done. Instructions have to be fetched, data has to be fetched, the instructions get executed, and they get put away, or maybe the data gets put away back into memory again. So all that has to happen, it all has to be done by the engine inside the CPU. And we can think of the CPU as containing the resources needed for giving effect to the instruction set. For example, if an instruction set contains a multiply instruction, it has to have the hardware that will do multiplying. If it's got a thing called a barrel shifter, if it's got a fast shift instruction, it probably has to have a piece of hardware called a barrel shifter in it to do that very quickly, and so on. Now we're not going to get involved in that hardware, but I'm just saying it has to be there. Okay, so together all the instructions that the 68,000 or that the machine, the CPU, is capable of executing are called its instruction set, and it's finite and it's small. Okay, so that means that you can't go along and while you're trying to write a program, dream up an instruction and say, oh, I think I need an instruction that multiplies by 2.5. Sorry guys, all you've got is the instructions that the hardware provides. Okay, now I'm being trite there, but nevertheless, people sometimes come on and say, oh, I thought we could invent any kind of an instruction. Okay, so the instruction set is the set of instructions that a particular make of CPU, a particular brand, a particular version of a CPU can recognize. So way back, like I was saying yesterday, the early computers had their own instruction sets. The IBM 360 was the first family of computers. Okay, whereas before the IBM 360 came along, you'd bring out a new computer, your IBM or Honeywell or General Electric or one of those. You bring out a new computer, and depending on the way you built that computer, and depending on the hardware resources you put into it, it'd have a particular instruction set because there's such an intimate connection between the instruction set and the hardware. In the IBM 360, they separated the hardware from the instruction set. And what they decided to do, presumably for corporate reasons, was to have a fairly fixed instruction set with different hardwares to implement it at different levels of performance, different speed or different cost, and so on. So the IBM 360 was the first time the idea of, and you'll probably come across it when you're out in the web, an instruction set architecture became a new idea. The instruction set architecture being distinct from the hardware architecture underneath it. Now once again, we in this course are not going to drop below the instruction set architecture. We'll be looking at the instruction set architecture of the 68,000. We won't really be looking into how it gets implemented underneath. But in different models of the 68,000 family, it gets implemented using slightly different forms of hardware. Just to go back to this idea of shifting, if you have a whole load of bits together in parallel, say 32 bits, and you want to shift them off to the right by 4-bit positions, you could either do that 1 bit at a time, taking 4 shift operations, and you could use the hardware for that, which would be relatively simple, or you could employ a barrel shifter, which is quite complicated and could move any number of bits in one go. Right? As far as the instruction is concerned, the instruction gets executed, but as far as the hardware is concerned, it'll either take 4 times longer if you don't have a barrel shifter, or it'll be much quicker if you do have a barrel shifter. Those kind of details are left underneath the instruction set architecture then. Anyway, so that's probably going a little bit too detailed at the moment. So a machine language program is actually the thing that you get from your compiler. You compile your, say, C program or your C or your C++ program. It gets turned into eventually a file of machine code, which is a machine language program, which will be loaded and executed by the machine. Okay, it's a set of instructions which utilize the CPU's resources, okay, to perform some specified tasks on data. It's very easy to forget about the data here. We're talking about instructions, we're talking about instruction executing hardware, we're talking about fetching instructions, but the data, how do we deal with the data? We'll come to that as well. Okay, memory. It's just a mechanism which information can be stored. And all you can do with memory is read information from it, and you need to know where it is somehow. You need to know where the information is. You need to know it's what we call its address or its location. So you can fetch information, and you can store information if it's RAM. Okay, you can store information, so you can read and write information. What you can't do in a von Neumann architecture is do anything out there. You can't say, take that number that's in that location and that number that's in that location and add them together out in memory. If you want to do something with them, you have to bring them into, you have to bring copies of them into memory, into the processor, perform the operation in the processor, and then possibly put the result back out there. Okay, so it's quite complicated to actually perform something as simple as just adding two numbers. But as far as the construction of the machine is concerned, memory is just a place where stuff gets stored and retrieved from. So it makes it easier to build memory. So nowadays, you can relatively cheaply buy an absolutely enormous amount of memory, say a gigabyte of memory, which is probably more computer memory than was in the country of Ireland in 1985 or 86. I mean, it's an absolutely phenomenally large amount of memory. But it's not enough. It's never enough. What's going to be in memory? Well, as I said earlier, two kinds of things. Instructions, which form a program, and data. Now, when you look at memory in a typical computer, there are these tools that you can use to actually look at memory. These little programs you can use to say what's at this location and what's at that location. If you look into memory, all you'll see is binary patterns, bits. And you won't be able to tell a priori whether a particular sequence of bits in some part of memory actually correspond to data or instructions. Okay, so from that, at that lowest level, I think it's fair to say no modern computer is typed. You know data typing in C and Java? No modern computer has data typing built into its hardware. There's a little bit of distinction made between instructions and data. And due to the problems with Microsoft Windows, these things have come to the fore recently. But we'll talk about them in the context of the 68,000 a little more later. Okay, but instructions and data is what's going to be in memory. Now, peripherals then are just these devices that are external to the computer system. So from our grandiose point of view, a computer is the CPU, memory, the peripherals looking from the inside, the bus that joins them up and over which information is transferred, and then there's all this other stuff, these peripherals that are out there. And the peripherals actually might be fairly sizable things. So many years ago when I started working in this business, a telephone exchange, a complete telephone exchange, well, that was a peripheral to a computer. So you had this computer in a room which would be, let's say, a quarter the size of this room, and it was driving a machine that was probably, could have been the size of the whole museum building. Okay? And yet, from the point of view of the programmers of the computer, it was a peripheral. Now those days have, I think, more or less gone. Nevertheless, still peripherals are considered, out there by programmers. Oh yeah, sorry, and just I did say peripherals make it the machine. If you look at a machine and you say, well, that's a machine that's a mobile telephone, for example, or this is a machine that happens to be the engine that moves a car along, and this other machine happens to be a desktop computer, and so on. The difference between those from a computational point of view is usually quite small. They'll all contain digital von Neumann computers, which will have, a CPU. They'll have memory. They'll have a bus system of some kind. And what will distinguish those machines from one another is the nature of their peripherals. But they'll all be run by von Neumann machines. So that's why I said peripherals make it the machine. Okay. The CPU that's in this thing here is a CPU that was designed by Motorola, IBM, and Apple, more or less in that order. Well, actually, probably IBM were the lead designers. And the CPU in this, versions of it appear in car and truck engines, in some PAM devices, and so on. Okay, so the actual machine itself is determined by the peripherals, but it's still the same computer. You'd still be able to, if you picked up assembly language for the PowerPC chip that's in this, you would find it fairly straightforward to program in any of those machines. Right? You'd have to learn the details of that area, but that would be it. Embedded computers are simply computers that happen to be inside a machine, such as in a mobile phone or something like that, a washing machine, whatever. One of the things that's very important in the context of embedded computers turns out to be energy consumption, power consumption, for a number of reasons. One is the size of the battery and battery life, if it's a portable device, but also the amount of heat that is dissipated has to be dissipated into the environment, and if there's a lot of heat being generated, it's going to require special measures, such as perhaps a fan or something like that. And you have to be very careful about that, and it's a real big deal in some areas. And it means that when you're programming those devices, when you become skilled in programming, you might want to program them so that they execute the minimum number of instructions, okay? So that the machine can go into a quiescent state and consume little or no energy while it's resting. Okay. To go on with our terminology a little bit, a microprocessor is a CPU on usually one chip nowadays. Okay. And so this is microprocessor systems. It could be called computer systems. This course could be called computer systems. When microprocessors came out first, they were very primitive, and there was a huge gap between a microprocessor and, say, a mainframe computer. That's gone now, and most computers would not be the architecture of most mainframe computers now would not be much different at all to some advanced microprocessors. So that's a microprocessor, and then a microcomputer. A microcomputer, well, a single chip microcomputer is all the von Neumann machine plus some of the peripherals typically on a chip. So it'll have the CPU, it'll have memory, it'll usually have a mixture of RAM and ROM. It may have some special purpose peripheral interface chip devices. For example, an analog to digital converter would be typical enough. And they'll all be integrated onto one chip, which you'll be able to buy for 50 cents or $1 or whatever. Okay, so that's a microcomputer. So that's what's before us, to get skill in these areas. Now, I think the first thing that we need to look at is number systems, right? Because we're going to be talking in